It's my immense pleasure to introduce Dr. Jessica Tierney, or Jess as she goes by. And the last time we did this, Jess, if you recall, it was at UTIG more than 5 years ago now. We were just about beginning to kind of collaborate at the time. So it really is a treat right now to be able to introduce Jess in the capacity of a colleague as well as a collaborator. Quite simply put, I was thinking about how to introduce Jess, but she's worked on several different domains, and her research spans several aspects of climate science. And so I kind of converged on trying to just say that Jess's work over the last 10 years has really revolutionized our field of paleoclimate. There's no other way to think about this, particularly for the Quaternary realm, but she's pushing back the boundaries, going back well into the Mesozoic as well, and the Phanerozoic. And so her work really has kind of scrutinized the relationship between what we think we know about proxies, what we think we're able to extract and measure from these proxies, but also to quantify that relationship with how much do we actually know about them. And towards this is not an easy task. You need to get into the nitty-gritties of the physics and the biology and the chemistry of these different types of proxies. And what Jess and her group has really done is dig deep, not be afraid to get dirty into the proxies, but also really connect it and make those sort of advances in uncertainty quantification and the statistics of these proxies into the realm of climate science and big picture paleoclimatology. And so over the last couple of years, Jess has really enabled the marriage of models and data in a seamless manner and in a way that's really innovative. And I think we're going to be seeing glimpses of this in this talk today. And I can go on and on about Jess's accolades and awards. I'll just simply say that she was a McIlwain recipient. She's already an AGU fellow. And amongst other things, she was the recipient of the Packard Fellowship fairly recently as well. Jess has published N number of Nature science papers, but also equivalently several papers in GCA, in EPSL, and so on, which are also extremely well cited and add to the sort of the nuances and the debates in our field. So with that, Jess, why don't you take it away and go for it. I'll be moderating questions towards the end, and people can either raise their hands and ask on video, or just type your questions into the chat. All yours, Jess.
Oh, thanks, Cal. That's really generous introduction. So thanks for the kind words. Yeah, so just as a little bit of technical advice, so I'm not sharing my screen. I'm going to be in front of the slides the whole time. I like to do that so I can actually see your faces a little bit better. So if you want to make me big screen on your screen, you can go into speaker view, and then I'll occupy the biggest screen. You can also, if you go to the upper right-hand corner of my panel, up on the panel, and hit the 3 dots and click pin, that will also make me sort of centered on your screen. And then you can make me as big or small as you like. So a little bit different from normal, but this way I actually can see you, and I can also see the chat box. So this is the way I teach, actually. So welcome to my class. But today's class is going to be on the Last Glacial Maximum. And this is my quaternary home base. I love the LGM. It's something that, I scientifically grew up studying. And so this study, which is actually the result of 5 years of research and a lot of technical development, was really enjoyable because it takes us back to, I think, sort of one of those origin questions of paleoclimate, which is how cold was the last glacial maximum? And I just want to acknowledge some of my co-authors here, in particular, Zheng Zhu, who's a climate modeler at NCAR, is responsible for the climate model simulations I'll show you today and did a fantastic job. My student, Jonathan King, wrote the code that we use to do the paleoclimate data assimilation. And my former postdoc, Brewster, also contributed to that code and was a big part of compiling the data. So let's go back to the last glacial maximum and familiarize yourself with what it looks like. These are the boundary conditions that we're talking about. This is what the world looks like. It's not a long time ago for us in geology, right? We're talking about 21,000 years ago. We know greenhouse gases very well. We get those directly from the ice cores. we have a good understanding of the extent of the ice sheets at the LGM in the Northern Hemisphere from moraines. We know the sea level was 120 meters lower. And for this reason, the fact that we know the LGM so well, the boundary conditions of it, and the fact that we have a ton of geological evidence, we can still use a radiocarbon system to precisely date things. And on top of that, the change in climate is actually really large compared to pre-industrial. It's always been, one of those time periods that has gotten a lot of attention in paleoclimatology. And because of these big changes in temperature and CO2, it's also an opportunity to investigate the quantity that's called climate sensitivity. So we look at the change in CO2 here. It's on the order of 100 ppm, which is really large, right? From 180 to 280. And so if we know that very well from the ice cores, if we also know the change in temperature from the LGM to pre-industrial, we can calculate the climate sensitivity metric. So as a reminder of what this metric is, which is an obsession of sort of modern climate change scientists, it's the response of the Earth's global temperature to a doubling of CO2. So basically, this is often computed in climate models, and what you do is you double CO2, you wait for the short-term climate feedbacks to settle down, changes in snow and short-term changes in ice, and then you measure how much the planet warms. And so the units here are going to be in degrees C, corresponding to doubling of CO2. And you also see these sort of probability distributions like this of this metric. So it's a probability density function. And you can see that the peak, it tends to be around 3 or 4, in a lot of different ways that we calculate this. And so the reason that climate sensitivity is an important thing is because it ultimately determines our future, right? We're gonna experience higher CO2, and that means we're gonna experience global warming. But how much global warming will we experience? It depends on the equilibrium climate sensitivity of planet Earth. So if we go back to the IPCC AR5 range, which is the blue bar on the left here, we can see that it's basically, the box of this box plot is 1.5 to 4.5, and then you can see the error bars are kind of extending out. It's a pretty wide range of values for climate sensitivity. The models that participated in the last IPCC assessment are denoted here as the CMIP5 models. And so they informed some of that IPCC range, and you can see they range between about 2 to 5 degrees Celsius. And then we go over to the CMIP6 models, this red bar here. And the CMIP6 models, as you notice, the red bar has moved up, and it actually spans between 3 and 6 degrees for double CO2. So a lot of the CMIP6 models, not all of them, but many of them have a higher ECS than their predecessors. And this is something that has been widely discussed in the climate community because the question is this high climate sensitivity actually justified in these new generation of models or not? And just to show you the difference that ECS makes, I'm going to show this example from the French model, CNRM. So what you're looking at here in the wiggly curves here is a comparison between their older generation model, the CMIP5 model, and that's going to be these lines like the one right here above my finger that don't have error bars around them, the single lines. And then being compared to their C6 equivalent. These are different warming scenarios. So 2.6 is like, we get our act together, and 8.5 is, burn a lot. And you can start to see this, especially for the red lines, those higher emission scenarios, those two trajectories, the skinny red line and the fatter one, diverge. And so by 2100, if you have an ECS of the older CNRM model, which is 3.1, you end up with a warming of just above 4 degrees. But if you have an ECS of 4.6, you end up with a warming that's at least a degree warmer than that. So this directly affects our projections for how warm the planet will be at the end of the century. So let's go back to the LGM then. It's been studied for a long time, and we can go all the way back to the mid-70s with this really important paper that came out in Science then by the CLIMAT project, where it's the first paper to really spatially map out the the temperatures at the LGM. And they did this using mostly assemblages of foraminifera in the ocean. So behind me is sort of a map of temperature anomalies during the LGM based on foram assemblages, and basically hand-drawn contours of where the cold tongue would be and where the worm pool would be. And then you fast forward several decades to 2009, there's sort of an update of the spatial view of the LGM by the European project, a European project called Margo Project. So this is a European group. So they did the same thing. They used a lot of the same data from climate, but they also added in some of the newer geochemical proxy data into this. And they came up with like a new map with a little bit of a different averaging technique. And from the very beginning of CliMap, climate modelers and climate dynamicists in particular were really keen to use this paleoclimate as a reference frame to understand climate sensitivity. So here we're looking at a paper from 1985 by Suki Manabe and Tony Broccoli from GFDL. And in this paper, they basically have two versions of their model, one that has variable clouds and one that does not. And they want to understand which one actually matches the data at the LGM better. And this is a pull quote from the paper above my head that says, an attempt has been made to use paleoclimate data from the last glacial maximum to evaluate the sensitivity of two versions of our model. Now, the key of that sentence is an attempt has been made. So they made an attempt, but it wasn't necessarily successful. And one of the reasons that it wasn't successful is because the data still had a lot of uncertainties, and it wasn't actually clear which pattern from their model matched the proxy data at the time. So these guys were way ahead of their time, but they were trying to do, exactly what we're talking about, is use the LGM as a way to estimate climate sensitivity and compare it with models. All right, so if we go back and like tour the literature just a little bit, and I'll take myself away. Oh, that didn't really work, did it? Well, then I won't take myself away. To look at, the differences in global cooling that people have come up with over time, we can see that there's been a wide variety, right? So this y-axis goes from basically -2 out to -9 degrees Celsius or so. And if you consider the error bars, and this led to the IPCC and the AR5 giving a 90% range of global cooling of -3C to -8C, okay? So that's actually like, it's pretty big range. And so if we take that range from previous studies and we try to estimate climate sensitivity from it, we get like a huge range, which is between 1 degree C and 6 degrees C for ECS, okay? And this range is like everything from like, you can't really have 1, and 6 is like really high, right? So that's world on fire. And so that's like not necessarily, a reasonable value for ECS either. So this is, I mean, the end analysis is really that, we're not able to, with these existing estimates of LGM cooling, we were not able to actually, there we go, I figured out how to take myself away so you could see the slides better. We're not able to actually constrain ECS that well. All right, so we're gonna revisit this problem now, and we're gonna revisit it with new stuff. So new data, brand new data collection, model simulations, and new statistical methods that allow us to combine proxies and models together and re-examine this problem, classic problem. So let's take a look, first of all, at the new data. And the thing I want to emphasize here with this new data is, well, a couple of things. First of all, we're only using the geochemical proxies for sea surface temperature here. And we're not using the foram assemblage data. For those of you who are familiar with these data types, the reasons that we did that are basically that we don't have, as you'll see, formal Bayesian proxy models for those types of data. Nonetheless, we have a huge data collection. This took several years to compile with help from undergrads and graduate students. And so we have 4 different types of data: O18 of foraminifera, magnesium calcium of foraminifera, UK37, so that's the alkanone paleotemperature proxy, and then a small amount of Tex86 data. Over almost 1,000 data points per time slice, the LGM time slice. And then for comparison, we collected data from the late Holocene time slice, that's at 0 to 4K time slice right there, so that we could calculate the anomalies between these two slices. So, and then model simulations, as you'll see, are key to our plan here because we're going to use them in a data assimilation fashion. And here's a shout out to Jung Zhu at NCAR who put together these simulations, really fantastic simulations with ICSM version 1.2 and some simulations with 1.3. And the key part of these simulations, as you can see kind of behind my head, is isotopes. We have water isotopes fully coupled in the ocean and in the land. And this is great because the O18 foraminifera actually form about 50% of our proxy collection. And so we definitely want isotopes in the scene so that we can, infer temperature. And the isotopes allow us to account for changes in the O18 of seawater that affect the proxy data. All right, so now about the statistics that we've put together. There's sort of two prongs of this. So the first is our Bayesian calibration models, which collectively, we call the Baywatch suite, BAYSPAR, BAYSPLINE, BAYFOX, and BAYMAG. And these are a Bayesian forward model for each of those proxy types that I just talked about that basically translates, they work in the forward direction. So they're going to take sea surface temperature, salinity, O18 is seawater, and then produce, how does that translate into a value of O18 of calcite? How does it translate into a value of alkanon UK37? And with full uncertainties on all the parameters in those models, with the error variance uncertainty, so we can actually propagate uncertainty in a really robust way. And these are all publicly available models on GitHub, in MATLAB, and many of them have been translated to Python now. And then this is the technique that we're using to combine. We're going to combine proxy data with models. And the reason to do that is that ultimately our data are not evenly distributed in space, right? So you could see like over here, just, looking at that bottom plot of the proxy data, they're kind of clustered near the coasts and they're not evenly distributed in the ocean basins. And that's normal because these data are coming from marine sediments and, to capture the LGM, you need a decent sedimentation rate, which you're only going to find on the coast, right? So that's where the data are. We can't work around that. What we can do, though, is get a more spatially complete view of the LGM by combining the proxy information formally with model simulations using this data assimilation framework. So I'll just walk you through the framework. It's offline Kalman filtered. So this is a method that is used really commonly in weather prediction. Offline means we're not rerunning the model after we assimilate the proxy data. Instead, we start with an ensemble of model simulations that we've previously computed, and then in ensemble sense, do the assimilation. So we have like 40 ensemble members and we do 40 different assimilations. And then we look at the average of that in the posterior field. And we do that because, at this time, we can't actually use the Cheyenne supercomputer to run CSM online and actually assimilate proxy data. That would be a lot of time. And so in the data assimilation world, we start with a prior state. That's where you're starting. Starting point is the climate model, right? It's our best guess at what the LGM looks like. And then what we're going to do is we want to add in information from the proxy. So let's say we have a UK37 proxy, and I'm just going to call that Y. What we're going to do is we're going to forward model using our Bayesian forward models. This would be BAYSPLINE in this case, to produce an estimate of what UK37 would be at the same location of the proxy. And that's Y estimate. So we're taking SST from the model, turning it into a UK37 value. Now we can compare the data and the model in the same space. The difference between them is called the innovation. The innovation is what updates the prior state. We literally add that innovation to the prior state with a weight, which is the Kalman Gain, and then we end up with a posterior state here, which is just denoted X2. So just to run you through what that K is, that's the Kalman Gain, it's a weight. And the numerator of the Kalman Gain is basically spreads the proxy information to other locations and variables. So it's the covariance between the prior state and the forward modeled estimate of the proxy. And then the denominator is basically the error. So it's the variance associated with your prior ensemble state, YE, estimate, plus the proxy uncertainty variance, which is R. And so to put that in layman's terms, there it is on the right. This is the relationship between the forward model proxies and the prior state everywhere else. So that spreads the information out. And the denominator is error. So if the error is big, right, then the Kalman gain becomes small and you don't update the state very much. Conversely, if your proxy is in a place that doesn't have very much to do with any place else, then it's not going to influence the field very much. So here's sort of a diagram of how this plays out. So the covariance, you can just think of it as a correlation. So let's say we had a theoretical temperature record in Seattle, and I'm calculating the correlation between that record in Seattle and Northern Hemisphere temperatures. And so I've got that red blob where they're positively correlated. And then there's a negative correlation blob out there, which is informed by, Pacific dynamics. And so if you had a proxy at this location, you would get information about both the red areas and the blue areas, right? So you spread the information out. So this way we can take the information from proxies that are at one place and spread it out to other places using the model covariance as a guide. So let's now look at the results. Okay, so we're looking here at mean annual changes in sea surface temperature on the left and on air temperature on the right. And so we assimilated sea surface temperature data only. We didn't assimilate data on land. That's because, basically out of convenience, we didn't have all those proxy forward models for all the possible terrestrial temperature proxies. And so this is the field. That field on the left combines what the model thinks happened in the LGM and what the proxies think. And then because SST and air temperatures are really intimately related, we also can get a posterior field of SAT, which is what you see on the right, which does give us a sense of what temperatures were over land, even though we don't have proxies there. This is going to be informed again by the fact that we are assimilating proxies in the ocean. The ocean is 70% of the Earth's surface, and so we do have some predictability even where we don't have proxies. So I'll just compare our results to those previous products that I mentioned at the beginning. Here's our data assimilation field on the top, and I'm comparing it to the original CliMap result. And then also that Margot result from 2009. They do have some similarities. So all of them seem to have deeper cooling in the North Atlantic. All of them seem to have some sense of North Pacific cooling, although our anomaly is a bit more severe than some of the other proxies reconstructions. The major difference is that CliMap and Margot both have these really weird features. They're like warm gyres, especially in the Pacific. And this feature has been criticized for a long time. It comes from the transfer function data, which we're not using in our assimilation. And it's been very hard to explain how you might get warm gyres during the LGM. It's not something that you see in model simulations. And we don't see that borne out in either the data or in the models in our data assimilation. Note too that, Margot has these very strange geometric shapes. That's because they're basically using kriging to infill between data points. And CliMap looks a little more like climatologically reasonable, and that's just because they use hand contours. But I guess the point here is that in terms of the spatial patterns, Margot wasn't very good at that because it didn't have a spatial model. The spatial model in CliMap was, what does the ocean look like? Let me draw it. And the spatial model in our case is the covariance from the models. So a little more dynamically consistent. I want to point out some features of different places around the world that kind of tie into some of the other research we've done in the LGM. So I'll start with the tropical Indian Ocean. So I'm just zooming in here and showing you the SST field. So this is the LGM change in the LGM relative to the late Holocene slice, the 0 to 4 slice. And the dots show you all the individual proxy data sites and what they say about temperature on their own, so outside of the assimilation. And here we see the field that's underneath here actually does a decent job of reflecting what the proxies would say. Again, a lot of our proxies are coastal, and so you expect some noise associated with that. But we see this really distinctive pattern in our posterior field of deeper cooling in the Eastern Equatorial Pacific, and then less cooling in the Eastern Equatorial Indian Ocean, and less cooling in the Western Indian Ocean, and then slightly deeper cooling again in the Arabian Sea. And this is a pattern that that Cal and I spent a long time studying, along with our colleague Pedro Dinezio, that we think reflects the response of the tropical Indian Ocean to the exposure of the Sahul and soon to shelves during the LGM. So because sea level is 120 meters lower, you have this huge shelf exposure in the deep tropics. And it turns out it alters tropical convection. You get essentially anomalous descending motion over the Sunda area, ascent over the Sahul shelf. And this change in the Walker circulation produces this pattern of cooling in the Eastern Indian Ocean and warming in the West. It's basically a weakening of the Walker cell in the Indian Ocean. And you also see a change not only in the SSTs, but in the model simulations and the thermocline with shoals. And so we've known about this effect for a while, been studying it for the last 7 years. And so it's nice to see that our data simulation product actually has that feature as well, because that agrees pretty well with what we know is happening to the Indian Ocean already. Now, if we go over to the Pacific, the story is a little bit different. So if we look at the field is underneath of that's the data simulation product. And then the dots are the actual proxy data. And so one of the things that's kind of curious here is there's decent agreement in the warm pool area over in Indonesia. It's mildly colder. Note that there's even one dot over there that says it's slightly warmer. That could just be proxy noise. But the weird thing is in the Eastern Equatorial Pacific, we have actually quite a few proxy data points, but none of them are really as cold as what our posterior state says. And so a lot of this deeper cooling in the Eastern Equatorial Pacific here is coming, one, from the CSM model that likes to do that in the LGM, but also probably from teleconnections to the California margin. So if you look up along the California there, you'll see some darker blue dots and darker blue changes in SST. And it cools a lot in that location, and that actually shares a lot of covariance with the Eastern Equatorial Pacific. So it could be that those remote proxies are also influencing the result here. But it remains to be figured out why we don't see much of a raw response in the proxy data here, whether this is a proxy issue or something else, and something we still have to look into. Just want to sort of describe what's going on in a dynamical sense. To do that, I'll show you a figure from Grace Swindler's upcoming paper, which is in revision at Paleo. And it shows nicely the changes in the Walker cell that are occurring in the LGM that kind of drive this difference between the Indian and the Pacific. So in the Indian, we see a weaker Walker circulation, but in the Pacific, that pattern of intense cooling in the EEP reflects a stronger Walker circulation. So we're just looking at vertical velocity here, changes in the ascent or descent of air. The top shows you the full simulation. This isn't from a simulation. This is just the simulation straight from the model. The yellow area indicates increased descent over essentially Peru, which is the normal descending part of the Hadley cell. Ascent over the Western Pacific, that's that light blue streaks. And then you can see the Indian response that's way over there. You see that deep blue indicating anomalous ascent over the Western Indian Ocean, and red as anomalous descent or dry conditions over the Sunda Shelf area. Now, if we run a simulation with just greenhouse gases, we can reproduce, it's the middle panel here, we can reproduce what's happening in the Pacific more or less, but we can't account for the Indian Ocean change. And then on the bottom, this shows you when you just change sea level and ice sheets, that's where the Indian Ocean change is coming from. So you can imagine you add these two panels together and you get the end response there, which is a decoupling of the Walker cells during the LGM, which is cool. And I could talk about for a long time, but that's another talk. All right, so let's go back to data assimilation results. Another cool thing I want to point out is relatively not so cold conditions in Beringia. And so if we look up to the northern high latitudes, there's this area in Alaska, okay, that isn't glaciated. And we already know that based on moraines and stuff, that central Alaska remains unglaciated, or, it remains open during the LGM. In spite of the fact of being really close to the Laurentide ice sheet. And so the question is, why is that? We've observed that. And so here you can see our assimilated field of surface air temperature with the ice sheet kind of superimposed on top of it, and very light blue colors in central Alaska, also in Siberia, even a slight warming in Siberia. We're able to reproduce this pattern of Beringian warmth. Pollen data also suggests minimal cooling in central Alaska. So this kind of fits with what we know on land. It also fits with dynamical expectations. Some of the work that Marcus has done in the past showed very nicely how this phenomenon can arise due to the way that the Laurentide ice sheet changes atmospheric circulation and actually affects cloudiness over central Alaska. And it turns out there's a huge reduction in clouds over central Alaska. You can see it here in his 2016 paper. That allows that area to, warm up. So more solar radiation is coming in and it's warming up. And it's also very dry there, I should add as well. So very dry, not so cold, creates this basically unglaciated valley. And incidentally, this is the place where humans crossed over, right, from the land bridge over into North America. And some of the earliest occupation sites are located here that date back to about the Bowling-Ellerod or so. And they went and occupied that unglaciated valley. So kind of a cool connection to human history. All right, so how do we know that anything that I'm telling you is true beyond, I mentioned that, it matches, some things match with previous expectations and other things, maybe not, like the tropical Pacific. One of the ways that we got at validating our results was to compare an independent proxy to our assimilated field. So a proxy that we didn't assimilate. So it's kind of like a test to see, how well did we do? And so the proxy that we chose for that is 18 of measured proxies for the 18 of precipitation. So both ice core 18 and speleothem 18. And so the map on the right shows the location of speleothems and ice cores that have LGM data and also have late Holocene data, so we could calculate an anomaly. That's sitting on top of the posterior simulated field for the 18 of precip. So we're getting this field out of the assimilation. Again, we did not assimilate any land-based 18 data. We only assimilated 18 of seawater. So anything on land is independent. And you can see that we actually do a pretty decent job by that cross plot there on the left, which shows the observed change in 18 from the ice cores and the speleothems, and then compares it to what we get from the data assimilation. And the R-score is about 0.67. So it's pretty good, all things considered, considering this was completely left out of the assimilation. And importantly, it's a big improvement over the prior. So if I flip now to the prior state, you can actually see, especially with the ice cores, a huge difference. So the prior, that's straight what the model says, right? So if we compare the model straight to without assimilation, we get a bad comparison between Antarctica and Greenland. You can see that they're really spread out there in that plot. Speleothems are not too bad, but then, again, going back, you can see how well that tightens up with the inclusion of proxy information from the ocean. There is an improvement in the speleothems as well. It's less of an improvement. They move less than the ice cores, and there's a smaller range of speleothem. The speleothem data are a little bit smaller in range, and I can talk about the reasons why it doesn't move that much. But the ice cores move a lot. So this actually means, what it means to us is adding in the proxy data for the ocean pushes us closer to the real LGM state, which is what we're hoping to do, right? Okay, so let's go back to these global metrics and build towards climate sensitivity. So because we have a spatially complete field, we can calculate the global cooling, okay, the LGM change in SST and the LGM change in GMST. Showing you 3 bars here. So on the left is, we did this in 3 different ways. In the middle is the DA result, and that's the result we're ultimately interested in. That's a combo of the proxy data and the model. But I split out what the data say and what the model say respectively so you could compare. So looking over at the GSST data for a second, what you can see is that the data suggests about a -3-degree cooling. The model has a huge range of possible change in GSST. And so you can see by combining them, we kind of narrow down the possible cooling range to around -3. It's close to what the data say. Now, if we look at the global mean surface temperature change, we can see that the data alone would suggest something around -5.5 degrees. In order to translate SST to GMST, I have to make a lot of assumptions, and that's why the error bar in that data only estimate is pretty large. And then we have the model on the right, and you can see how the DA is kind of a combo of them both, giving us that value of -6. So, returning back to our estimates of global cooling that are in the literature, this sort of span here again that sort of spans the space between -2 and -8 degrees. We can now like really improve upon that and narrow that down with our DA estimate. This is where our DA estimate falls. That's the 95% confidence interval of it. It's pretty tight. And fortunately, it does agree with all 5 of those studies on the right, which is comforting that others are getting a similar value, especially that BE18 on the far right. That's based on noble gas data, so it's totally independent. And they're also getting -6, but we have much narrower uncertainties. And so anyway, we can update this now and say that, yeah, this is really -6C. We have a much tighter idea. That's the global cooling that we're after. Okay, so now using this updated estimate, now my mouse isn't working, of global cooling, we can go and make the calculation for climate sensitivity. So ECS, equilibrium climate sensitivity, when we calculate it for paleoclimate, we set it up this way. The numerator is the change in temperature. We're getting that from our paleoclimate data assimilation product, right? It's at -6. The denominator is the radiative forcing. And we divide by that, and then we're going to multiply by the forcing associated with the doubling of CO2. This value we know fairly well. Okay, it's based on our understanding of physics of CO2, and it's around 3.8 watts per meter squared. So we know what that one is. We have a pretty good estimate of global mean surface temperature cooling. Now that denominator, the delta R, is a little bit trickier. There's 3 terms in there. One is the changes that are associated with greenhouse gases. So we have lower greenhouse gases during the LGM, obviously. That we know very well. Again, it's based on physics, but then also the fact that the ice cores give us a really precise estimate of changes in CO2 and methane and N2O. And so that has a pretty narrow uncertainty on it. The middle thing is the forcing associated with ice, right? So all of a sudden in the LGM, you've put these bright white ice sheets on. So you're going to change surface albedo. So that has a radiative impact. And that we have to get from modeling studies. There's no other way to do it. And so that value of -3.6 is an average across a bunch of modeling studies that tried to isolate that forcing. I'll show you in the next slide the distribution of that. And same for this last term. This is the forcing associated with dust aerosols. So it's widely thought that the LGM was dustier, it's drier, and we actually have quantitative dust records that show that flux is amped up. So we expect that to, from the direct effect, have a cooling impact, to have a sort of a negative watts per meter squared and help contribute to LGM cooling. Now, when we actually look at the distribution of the radiative forcing of ice and dust, we find that there is a pretty big variety across models. And so these are these histograms. They're kind of poorly populated histograms because, to date, there's still not enough studies of this. You basically need to run single forcing simulations to calculate this out. And we did do it with CSM 1.2, and you can see in white, that's our estimate from partial radiative perturbation tests that places us in the middle of that right-hand pack of around between -3 and -3.5 watts per meter squared. There's some outliers though, MyRock, EPSL, MPI, that have a much stronger impact of the radiative forcing of ice. So it's interesting to see that they kind of cluster over there. Dust forcing is really interesting too, because there's a number of models that actually indicate that even though the LGM was dustier, it wouldn't have had that much of a radiative impact once you add everything up spatially. And so you actually see a number of models hanging out near zero. And the one that's all the way over to the left, that's -2, that's actually a really old intermediate complexity model. So we're basically gonna ignore that one. I included it in our estimate, but it's probably overkill. And so we sampled the uncertainty here. We included all these numbers in our ECS calculation and sampled the uncertainty as best we could to come up with our probability distribution. It's an empirical probability distribution of climate sensitivity. And this is what it looks like. And so you can see it's not the same shape as those distributions I showed in the beginning. We don't have anything that's actually going even down to as low as 1. So we don't really see that asymmetry. And this isn't, again, this is an empirical distribution. So we're not putting any constraints on its shape. Median value is 3.4 with a 95% CI of 2.4 to 4.5. And just to break down the uncertainty, because we've narrowed global cooling so well, it only accounts for about a quarter of the uncertainty in this distribution. Greenhouse gases are definitely, we know that one the best, right? So it's only 10% of the uncertainty. The big kahuna here is ice, I would say, which is almost well, a little less than half of the uncertainty in this probability distribution. And notice too the double hump feature. So that's coming from those two populations of climate models, one that are like, you know, when that you put ice sheets in them, they really react, and the other not so much. All right, so we get a value of 3.5. We calculated this in a number of different ways to test the sensitivity to different assumptions. And so in our paper, we have these sort of stripes, which recommend, you know, represent ranges of climate sensitivity, whether or not you include the dust aerosols. And the middle bar is what I basically just showed you. And this one actually is an assumption where we assume that the ice sheet forcing is actually not as effective as you might assume. What that means, the efficacy of ice sheet forcing, is basically the idea is that the ice sheets in the LGM may have affected the northern hemisphere a lot more than the southern. I mean, that makes sense. So its efficacy in terms of a forcer is not 1-to-1. It's more like 0.7-to-1. And there's some really emergent literature like looking into that issue. So basically, if this assumes the ice sheets aren't as effective, in that case, ECS moves up. But the center dot is really hanging out between like 3 and 4, no matter what you do. And so then if we go back to our plots here and compare our new estimates of ECS to the IPCC AR5, the CMIP5, and then the CMIP6, we can see how we measure up. We take our 99% CI, the light blue line, and it almost overlaps with all the CMIP6. Although it does rule out those extremely high values of like 6. More useful is to look at the 90% CI. That's really the center of the distribution. And there we find, you know, it's that those high ECS values may not be, you know, don't agree with the LGM state. That is what I should say. But you can consider the LGM, since it's a cold state, it's really like a minimum bound on ECS, because in paleoclimate, we expect that ECS actually increases in warmer climates. So a cold climate should have like the ability to constrain the lowest possible ECS. So we like to focus on the lower end of these bars here. And these bars like completely rule out an ECS of below 2, which maybe is not great news, you know, if you were gunning for a low ECS, because, you know, low ECS means we warm less. And we are really supporting this sort of middle value that's between 3 and 4, which incidentally is what Jules Tierney said it was in 1975. So I guess we've just come around full circle here. But older estimates of LGM climate sensitivity were giving some goofy numbers like 1.8. So it's nice to rectify that and get a result that actually we think makes a lot of sense. All right, so with that, I will say thanks, acknowledge our funding sources, and also a special thanks to Matt Fox, former grad student here, who actually worked quite hard to help me with compiling those thousands of data points. And I'd be happy now to take some questions.
All right, thank you, Jess. Let's see. We have ample time for questions, so you may feel free to raise your hand in the participants list, or just send it along in the chat and I can read it out, and then we can go from there. So any questions? We've got a lot of time here. So we have a question from Joellen Russell. So Joellen says, how does LGM equilibrium climate sensitivity averaged over thousands of years relate to modern transient climate response, where the deep ocean will not equilibrate for 300 to 800 years minimum?
Right, so those are different metrics, right? So in the IPCC world, we calculate ECS and then we calculate TCR, transient climate response. And transient climate response is a different metric. So you can't compare those two. And even in the historical data, they're calculated differently. So this is definitely looking at equilibrium climate sensitivity as an equilibrium with the ocean in equilibrium and everything in equilibrium. Interestingly, the new definition of ECS in the AR6 includes like full ice sheet equilibrium. And so we're starting to kind of blur the boundary between, there's an old boundary between ECS and ESS, or system sensitivity, which was like everything. But now they're starting to blur that boundary. And the new recommendation is actually that ECS should include ice sheet, even though it will take a long time for them to equilibrate. Yeah, so that's coming out in the AR6, which is interesting. But our value, I would argue, is comparable to, it's obviously a paleoclimate estimate from nothing's ever truly equilibrated, I would argue, even in the paleoclimate world. But it's a touch point that we can, compare to other estimates of ECS that use, for example, the historical record, and then do make assumptions about equilibrium one way or the other.
Okay, we've got two hands raised, but I think Warren had a question first. So I'm just going to read Warren's question quickly. Warren says, your model results show Beringia is not particularly cold during the LGM. However, model results show the North Pacific subtropical high is about 6 degrees C colder. So how robust is the finding of a very cold North Pacific subtropical high?
Yeah, it's actually really, that is another feature that agrees with independent paleo data that we're really excited about. So that cooling is, it's a little bit higher than the North Pacific high, and it actually represents an extension of the subpolar gyre in the North Pacific. So the subpolar gyre is actually shifting south during the LGM. And we have some amazing 4M-based data that record that shift and actually record how that gyre moves to the deglaciation in a paper that Will Gray published last year. And so actually that feature agrees perfectly with their analysis, which was done independently from a set of North Pacific cores. Now, the magnitude of cooling that we see is up for discussion, but that dynamical shift of the subpolar gyre just dropping south, I mean, that's in response to the way the Laurentide is shifting circulation. So, basically the storm track, the jet is farther south, and the subpolar gyre is also farther south, and that's what's driving that there.
Jack, do you want to go ahead with your question?
Sure. Hey, Jess, great talk. That was really cool. Thank you. As you were talking, I was thinking about how in complex systems, the, response function is highly dependent on its initial state, current state. And you did mention that it's thought that ECS would be higher during a warmer climate. And so I was wondering, could you talk more about that and what's the basis for that? And I don't know, I'm just really interested in that question.
Yeah, so our understanding from the paleoclimate record is if we look at high CO2 climates that if you, for example, double CO2 in a greenhouse climate like the Eocene, you get like a much higher ECS. And we think it's due to nonlinear behavior, especially with clouds. So the main thing that has been attributed to is feedbacks with low clouds, the stratostacks that exist both in the subtropics and in the polar regions. Basically, they start to disintegrate in high CO2 climates. And when they do that, then they let through more, sunlight, and everything heats up more. And so you get this like add-on effect. Another sort of similar, so there's a cloud paradigm that, will produce a nonlinear ECS. There's also something called the SST pattern effect, which, I mean, in a way, these things are linked, but that actually the configuration of the tropical Pacific and its effect on the energy balance, whether the Eastern Pacific is warmer than warms more than the West or vice versa, can actually have this sort of nonlinear effect on the energy balance. And so that's another way that you can get weird nonlinearity in ECS. In warm climates and models, we see that the cold tongue in the Eastern Pacific warms up more than the warm pool. And that actually causes this sort of nonlinear pattern effect thing. So those are the two big ones that people talk about right now as contributing to that. But we still don't know exactly how nonlinear it is. Like that really needs better paleo constraints to know.
Yeah, okay, thank you.
And Janjan, do you want to go ahead with your question?
Yeah, okay. I have two questions. So first, you showed that the PDF for the climate sensitivity is highly skewed in the previous estimate. It has a long tail. So in your new estimate, so the PDF becomes much more symmetric. So what caused that?
Yeah, so our PDF is completely empirical, right? So it's an empirical sampling of the uncertainty space, a Monte Carlo sampling in this uncertainty space. So we don't make any assumptions about the shape of that distribution, even though we do expect it to have more of that asymmetrical shape. We didn't choose to impose that constraint. So if you think that that asymmetry is a fundamental constraint on the distribution of ECS, then it would be worthwhile placing that constraint on it, on that calculation, which is actually what the CRP report that came out on ECS did. They actually, you know, in their it's like 100-page paper in Review of Geophysics, but they, you know, they actually force those distributions to be that kind of gamma-like shape. We didn't do that, and so what we're getting is purely like an uninformed thing. So I'm not sure I would like put stock on the shape so much, except that the bounds are much more narrow because we're ultimately constrained, you know, by the uncertainties in the global temperature, and also our best guess at the uncertainties in the radio forcing, and that's just what it comes out to be. But you know, I wouldn't say that our result implies that should be the shape of ECS. It's just the empirical probability distribution that we get.
Okay, thank you. My second question is, from your reconstruction, you showed that the cooling actually is amplified in the North Pacific and in the North Atlantic. So, so what's the mechanism for the large cooling in the North Pacific, for example? So it's, yeah, it's due to the current, or it's due to the sea ice over that region?
Yeah, I think I just answered that with Warren, but it's a shift in the subpolar gyre. And so the gyre is actually moving pretty far south. And so that front, which is a pretty strong SST front, is shifted. And so you create this sort of deep cooling there. Sea ice, I don't know if I could answer that. We didn't assimilate sea ice, so I'm not quite sure what it would look like. We probably should have assimilated it. We will do it in version 2. And then the North Atlantic, I think sea ice and heat transport is a little bit less in that area. But I haven't diagnosed the North Atlantic one very closely. Yeah, but the North Pacific one matches up with evidence from other proxy studies. So I think that the cooling is real. I just don't know about the magnitude.
Okay, thank you.
Andy had a question, but I think it's very similar to Jack's question. So we can skip past that. We have probably about 5 more minutes for questions. In the meanwhile, I'm going to ask a question, Jess. You know, I know you've refrained from, when we've had discussions about this, about how we should refrain from commenting on interannual variability when we're looking at mean states. But given the sort of the, you know, to some degree, validation of a cooler Eastern Pacific in your reconstruction in the data assimilation, would you care to comment about potential implications for El Nino and what El Nino might have been doing outside the inference that we already know from Zhang's work beforehand that CESM simulates a reduced ENSO? Do you think that this can contribute to some you know, type of model data comparison about ENSO?
Yeah, so I mean, we can't, as you know, we can't assimilate from mean state to interannual variability. So yeah, I was going to say that it basically does support, you know, our result supports Zhang's conclusions. But, you know, I want to point out the caveat that for whatever reason, the data in the EEP, you know, the raw data don't show like the deep cooling, right? And I have yet to figure out exactly why that is. I suspect there's something going on that I don't fully understand, to be perfectly honest. Because actually, you know, we threw out the assemblage data, but if you bring them back into the scenario, you know, Alan Mix showed in the 90s that if you use a sort of a better, you know, no analog technique or whatever, no modern, I don't know, whatever to deal with that, can't remember what the technique is, he gets a huge cooling in the Eastern Equatorial Pacific from the assemblage data, like massive, that matches our assimilation, which makes me think that there's something that I'm missing here about the EEP data. And so honestly, I don't feel comfortable making too many conclusions about it until we sort out the source of the proxy model discrepancy there, which is still a bit of a mystery to me. But if you just take it at face value and say, okay, our assimilation, like combine the model and the data, and this is what we get, then it does support Jung's idea that you should have reduced El Nino, and, you know, as you know, supports Heather's data to that extent, that El Nino variability should be suppressed in the LGM, you know.
Thanks, yeah. We probably have time for one more quick question if anyone's interested. And then after this, we're gonna have Marcus and Paul Cap's class where it's the discussion and people can stay on who are registered for that. Any other questions?
Great talk. Thanks for having it. Interesting.
Thanks, John.
I would unmute more, but there are barking dogs. Sorry.
I have a follow-up question about the much reduced temperatures in the high North Pacific and whether or not that leads to enhanced deeper water production in the North Pacific from what we have today in interbasin communication.
Yeah, well, you have to ask my colleagues James Ray about that, but I think that the current view from, I mean, I'm sure you know this, from radiocarbon proxies is that there is evidence for increased ventilation of the North Pacific in Heinrich Event 1. And people argue whether it's intermediate water formation or true deep water formation. But basically the radiocarbon ages of benthics and planctius come together closer in H1. The LGM, I don't think that there is a evidence for, certainly not evidence for full deep water formation. I'm not sure to what extent there's evidence for more intermediate water ventilation. But that would fit, I mean, this shift in the gyre, it does allow for that. So, you know, it's a possibility, but I don't think, I haven't checked, should check. I don't think that CSM has deep water formation in the North Pacific and the LGM, but it might have more intermediate ventilation. I wouldn't be surprised.
I will say that a paper just came out last week from Laura Robinson's group that James Ray is on that shows that there was persistent intermediate water ventilation throughout the deglaciation, including the LGM as well. So perhaps that ties in right there to that cooling right there. But
okay,
so
cool. Yeah,
let's give Jess a big round of applause. Thank you, Jess, for your time and for sharing your results.